Okay, guys, I guess we can start. So I'm going to, guys, share my screen. Do you guys see my screen?
Yeah.
Okay, great.
Yes.
So, I want to show you the power. Okay, here. So, guys, in the remaining of the lectures, we are going to talk about applications to complex problems. One of them is hydropower operation. Okay. I know some of you are not familiar with this. However, I will give you guys a background, so you guys don't need to know much. We will talk about the models. We will play with the models, and then we are going to apply optimization. Okay, so today we will talk about, guys, hydropower operation. If you guys have any questions, please stop me at any time. Okay, the basics of hydropower. Let me, guys, show you a video. I hope, let me see if I can, let me stop sharing, and then so you guys can also hear the sound. Okay, let me see if I can, I believe it's this one, and okay, stop sharing. And then what I will do, guys, is play this video. Okay, let me see. I can copy this. Okay, clap. Okay, so I'm going to share my screen. Okay. But stop share, because when I share, I have to put something, screen, advanced sharing options, and then, okay, so, do you guys know how to share the sound? Let me guys share.
Like if you're playing something?
Yeah, I mean, I would like to, oh, here, share sound, okay, here. Then share, okay. Okay, guys, so I'm going to play a video.
Hydropower or hydroelectricity.
Do you guys hear the sound?
Yeah.
Okay, great.
Refers to the conversion of energy from flowing water into electricity. It is considered a renewable energy source because the water cycle is constantly renewed by the sun. One of the first uses of hydro energy was for mechanical milling, such as grinding grains. But today, modern hydro plants produce electricity using turbines and generators. The mechanical energy created by moving water spins rotors on a turbine. This turbine is connected to an electromagnetic generator which produces electricity when the turbine spins. There are two main types of hydroelectricity production: dams and run-of-river. Hydro dams utilize the potential energy from dammed water to produce electricity. A dam is a large barrier constructed to raise the level of water and control its flow. The elevation created by the dam creates gravitational force for turning the turbine when water is released. Some dams also contain an additional reservoir at their base where water is stored to be pumped to the higher reservoir for release when electricity is in demand. This is referred to as pumped storage hydro. The second form of hydroelectricity production is run-of-river hydro. Run-of-river still uses turbines and generators, but relies on natural water flow rates of rivers, diverting just a portion of the water through turbines. Because run-of-river hydro is subject to natural water variability, it is more intermittent than dammed hydro. There are various sizes of hydro plants that produce electricity. Large hydro, greater than 30 megawatts, small hydro, 100 kilowatts to 30 megawatts, and micro hydro, less than 100 kilowatts. The Hoover Dam in the United States is a whopping 2,074 megawatts, which is enough to serve 1.3 million people. Of all renewable energy sources, hydropower holds the largest share of worldwide electricity production. Hydropower has several benefits. It is a cost-competitive form of electricity, even though the initial building cost can be high. It is quite reliable compared to other renewable options and pairs well with other sources as it can be used as baseload power. In some cases, dammed reservoirs can also help with flood control and be a reliable water supply for communities. There are also some concerns with hydropower, especially when it comes to large dams. Damming a river has a major impact on the local environment, changing wildlife habitats, blocking fish passage, and often forcing people in riverside communities to move out of their homes. In addition, dam failures can be catastrophic, claiming the lives of those living downstream. Hydro plants are also not completely free of greenhouse gas emissions. As with most forms of energy, carbon dioxide emissions happen during construction, particularly due to the large quantities of cement used, and plant matter in the flooded areas makes methane, another greenhouse gas, as it decays underwater. That's hydropower.
Okay, guys, so I wanted to share with you this video because kind of summarizes what hydropower is. So going back to the presentation, basically in terms of optimization, the idea is we should find out what should be the optimal flows passing through the turbine so we can maximize the profit that we make selling the power. So several companies, they sell the power to third parties. And of course, they want to maximize their profit, right? So, for example, during the morning, from 7 in the morning all the way up to 9, 10 in the morning, I think it's up to 9, the price of the power is much more expensive than in the night. In the night, when people are sleeping, 2 in the morning to maybe 1 in the morning all the way up to 5 in the morning, the cost of power is cheaper than in the day. Why? Because nobody uses the power. I mean, few people use the power, right? But during the day, you need the power for running, businesses, for running, for shower, for other purposes. So, but it's not only the variation during the day. Also, it's important, example, during the summer. During the summer, the power is typically more expensive because, you need to run air conditioners. But during the winter, it's kind of, also you have to use, the heater. So there is a different variability, but also it depends. You might have a water from the rain, or you might not have water. So you don't know. So you have to do forecasts, right? You have to do forecasts. So this problem is not simple. It's actually very complex. When I was at Oregon State, my group has developed the code for doing the operation of the whole Bonneville Power Administration, which basically sells power for California, Oregon, Washington, Idaho, part of Canada. So, and then I became interested in this topic. So what we will, guys, see today is, how to optimize hydropower. And I will show you a case study. And you guys will play with MATLAB, and then you guys will you can apply this, of course, to your particular case. If you have a hydro in other place, or you can. This is not. Yes, please. Yes.
Sorry. Are you recording the class?
No, I am not.
Oh, okay.
No, I'm not.
Excuse me.
So you guys have, by the way, you guys have the handouts in Canvas. Everything is in Canvas. You guys the code. You guys have the lectures, and everything is in Canvas. Yes, yes, Alice. Yes.
Excuse me. I have a question about this hydropower. This steps of hydropower damage the environment, I think, in a dry place. For example, in Iran, there are many of this hydropower energy that because of that rivers have not enough water for lakes, and lakes getting dried, and because of that, I think it's very damaging for the environment in dry places.
Yes, however, it also can have much more benefits. So you have to kind of understand this problem from multiple objectives, from multiple contexts. Because, example, dams are very, very important for multiple reasons. One of them is for flood control. So because you can store water during the rain seasons, what happens is whenever you have too much water, you can store it rather than going downstream. If you go downstream, you can flood areas and it can even kill people, right? So in some places, in China, in India, sometimes thousands of people die because of floods. Okay, and those happens typically because those rivers are not regulated. So which means that they don't have dams. If they would have dams, those people wouldn't die because the water excess would be captured in those dams. Okay, that's one reason. Yes, I agree. By building a dam, you also are creating environmental problems because if before you had a lot of fish, the fish will not be able to pass through the dam. So then there's going to be, of course, environmental impacts. Yes, there is a pros and cons on building dams. However, example I was saying about the benefits. One of the benefits in the U.S. of dams is that it helps for navigation purposes. So this is kind of what we study, of course, in high school, in college, about history of the U.S. One of the reasons of the great development of the U.S. is the navigation that happened in the 1800s, where there were products that were transferred from the coast to England, and the reason for that was because there were some small dams. So, right, the dams will increase the water in the rivers, and then they will allow the passage from barges and from large ships. Otherwise, there would be pass of ships only during heavy season, during kind of whenever there is a significant amount of water. But by having dams, you can have ships and large barges through the whole year. So there is many benefits of dams. I totally agree. There is a lot of environmental impacts, but I would say that the benefits can be very significant compared to the environmental impacts. And another benefit, which I think is happening right now and is going to happen in the future, because, example, many people say, why don't we use sun power, or why don't we use wind power? The main reason is the following: the wind power is not a continuous power, right? You will have a wind power only when there is wind, right? The wave power also, you will have a significant power only when there is significant wave activity. However, one of the trends that's happening in the last perhaps 10 years or 15 years is combining hydropower with nuclear, with sun power, and with wind, and with other minor forms of power. So whenever you want to have kind of a base load, whenever you want to maintain the base load, okay, you use the hydropower. And then whenever it's available to offset the variations, right? So actually hydropower is good for offsetting the variations. So whenever there is a lot of variation, for example, let's say you don't have wind. If you don't have wind, you can use hydropower. And then when the wind comes in, you can basically not produce hydropower. So So now, in the last 10, 15 years, people are using hydropower to kind of to balance those variabilities. So, example, sun power. Sun power, you cannot have sun power during the night, right? So some organizations combine, example, hydropower plus sun power plus wind power. So if the demand of sun and wind is enough, you don't use any hydropower. Now, if there is no wind, or if the if the production of power due to sun and wind is not enough, then at that time hydropower will kick in, and then it will, you will satisfy the demands of the population that you want to serve. So people are using hydropower as a base to kind of to handle the variability of the power due to wind, sun, and other forms of. So according to the literature and according to experience, hydropower and nuclear power are the most stable forms of power because they are pretty much constant, right? But actually, hydropower is even better than nuclear. And the reason is because in nuclear power, if you want to start the power, it takes time, right? You cannot just set up the nuclear power in 1 minute. You cannot do that. You need at least 1 day because you have to do gradually. You have to do the setups gradually. If you want to change in a nuclear power from one example, if you want to double the power for a nuclear system, you need at least 1 day to basically change gradually the setup. And also, if you want to reduce the power in nuclear, example, if you want to reduce the power to half, you have to do also gradually. In the case of hydropower, you can do this in a matter of seconds. You simply shut down the gate in the pipe, what we call penstock. The penstock pipe is basically, this is a penstock pipe. Okay? This is a penstock pipe. So if we simply, here we might have a gate here. If we simply shut down the gate, we can shut down the gate in a matter of literally seconds, right? And then you can have power or not very quickly. And if you open the gate, you will start to have hydropower. So this is very convenient. This is very, very convenient. Okay.
Yeah, I have a question because we should consider the lakes also, because if we don't have enough water in lakes, it's irreversible damage in the environment, because we have a lake in Iran. It's full of salts, and establish 20 dams in the river that reach to the lake, and it's also getting dry, because if it getting dry, it's spread salt to all the environment and getting the desertation.
Yes, I totally agree. Yeah, I mean, I guess those criteria has to be satisfied during the design and during before the construction of the hydropower. Those has to be evaluated. But here we are not talking about the environmental impact, which I totally agree. Some dams can create serious problems to a community or to even to a country. I totally agree with that. But in some places, especially when you have a lot of water, the dam or the reservoir, can do much more benefits than disadvantages. Example, in China, several dams can, like I said, can save the life of thousands of people, because Yeah, I mean, especially dams are good whenever there is a sudden variations of flow. So if the flow increases very, very rapidly, and then in that cases, those variations might kill people, right? Okay. So yes, but I agree with you, Abbas. Whenever we do this, we have to have a significant environmental impact study. Okay, so this is kind of the cross section, kind of a 3D view of the dam. This is so basically we have a turbine here. Okay, we have a turbine. So this is a penstock basically, right? This is a penstock pipe, and then after this flow comes here, then it will basically go downstream, and this is the tail race. This is the area, the downstream area, right? This is the upstream, and this is the downstream. So when we talk about the spillways, we have two types of spillways. Okay, we have two types of spillway. One is here, try to show the color here. So we have the spillway weir, and then we have a regular spillway. So sometimes we have whenever you have the spillway, you might have a gate. So this is a gate here, okay, and this gate, this is okay. So this might be a gate. So if you close the gate, of course there will be no flow. However, you can open this gate, and the flow will come out to here, right? So this is called regular spillway. This is with gates, so you can control this flow. Okay, we can control this one. Why we can control? Because we have a gate, right? We have a gate. Now we also have a spillway weir. What's the difference between the spillway weir and the regular spillway? The difference is that the spillway weir is typically this shape. Typically this shape. So this is the structure, and the water basically is. Let's see if I can. Okay, this is the water. So simply after the water level reaches to this crest, the water will simply spill. Okay, so this is called a spillway weir. This flow we cannot control. Why? Because the water, as soon as arrives this level, will simply overflow. Okay, this is overflow. So we cannot control because we do not have a gate. Okay, this is different than the regular spillway. In the regular spillway, we have a gate here. See? You guys have a gate. You have a gate, and then you can close it and you can open it. So you can control this flow. Okay, you can control this flow. So guys, whenever we have a dam, then we can control two flows. We can control two flows. What are those flows that we can control? The flows that we can control are the turbine flow, because I can close or open the gate here in the penstock, and also I can open or close this gate for the regular spillway. Okay, so we have two types of flow that I can control. The spillway weir is called uncontrolled flow because we cannot control, right? It's uncontrolled flow. Okay, you guys, any questions about that?
Yes, Professor.
Yes.
So this type of dams are always like this, or some other countries use different types of dams, or
there's only one? There's many types of dams, but this is kind of the general, complete type of dam. Some dams only have a turbine. They don't have this, and then they have a spillway weir. So every single dam in the US or everywhere, they have to have the spillway weir because this is kind of an emergency spillway. Okay, it's an emergency spillway. So it has to have that. Some dams only have the turbine flow. They don't have the regular spillway. Some dams have several several spillways. You can have multiple gates at different levels. Okay, so it can be more complex, but in general, there is three types of flow: turbine, regular spillway, and the spillway wheel. This is in general. Some of them can have a less. Some of them can have spillways at multiple levels in the dam. So you can have even several boxes in the same in the wall of the dam, basically. Okay. So, guys, any more questions?
Thank you, Professor.
No, thank you. Okay. So. So, guys, the water can leave the reservoir through the spillway or through the turbine, right? So there is only two ways: a spillway or through turbine. And spillways can be two types of spillway. Okay. The water that passes through the turbine can use or can produce electricity, right? Because we have the turbine there. And then, guys, the idea is that this power that enters, this power that is produced in the turbines we can sell that at a price of the market. Okay, so in the same way, guys, as you have a gas or you have a stock in the stock market, right, where the price of every stock is determined by the market, is the same thing for the electricity. Okay. The electricity that comes out enters to the network of electricity, and then the price is the price that you sell is the price of the market. Example: if you guys go to Google and you say electricity price in Florida, you guys will see that the price is fluctuating pretty much every, it's fluctuating pretty much every minute. So you can see the price is fluctuating. But we have a typical pattern. For example, during the day it's kind of it's more expensive, and during the night it's typically more cheaper. But even during the hour there is some variation. Okay, so the idea of the optimization is when we should produce power, when we should hold the water. Okay, so we can have a more, so we can sell the power whenever the price is higher, right? That's the idea. But also you have to consider the rain, because you might sell the power now or tomorrow, but in 2 days you might not have enough water in your dam. So now you are in trouble with downstream, because downstream will tell you, hey, you have to give me at least this amount of water for fish or for navigation. So you have to kind of optimize, taking into account many constraints. Okay, so that's the...
Professor?
Yes, please.
What happens if the lake behind the dam freezes?
That's a very, very good question. Yeah, so that becomes also a constraint. Actually, those problems are handled by the U.S. Army Corps of Engineers. In the case of the Pacific Northwest, whenever there is enough water and whenever there is no problems, the Bonneville Power Administration, they are in charge of selling the power. But whenever there is problems, all the authority of the Bonneville Power is lost. All the power automatically goes to the U.S. Army. Now the U.S. Army is responsible for making all decisions. Okay, and I don't know if you guys know, but example, in some cases, the U.S. Army actually can be in control of all the waters of the U.S. However, in most normal conditions, some organizations manage all the water. But in emergency conditions, the power goes back to the U.S. Army, and they have to make decisions. Example, there was a dam in Ohio that had to be, there was so much rain that, flooding was happening in the area of Ohio. So what they had to do is, and that flood that was kind of going downstream was going to flood an important city in that area. So what the U.S. Army did is they had to blow intentionally levees upstream, and they had to flood intentionally some agricultural areas, right? So they had to blow the levees. I remember I went to that area. I believe that it was like near half a mile of levees were blown, and there was extensive flooding of agricultural areas. And they did that because they wanted to protect the downstream city. So whenever there is problems, for sure, the U.S. Army will take control. So there is a kind of a communication between the management and the U.S. Army. So, I mean, now, if the lake is frozen, then of course, if you put extra water, then the water will simply, it will not flow downstream, right? It will simply create a backwater effect, and that might create extensive flooding. So in those cases, the U.S. Army has to make the decision. So here, guys, the optimization I am showing you is in normal conditions. We have normal conditions, and we want to make more money, right? We want to make more money by selling electricity. If there are problems like flooding, or there are problems of William mentioned of a frozen lake, then that decision will be taken care of by the U.S. Army. So probably what the U.S. Army would do is, okay, we have a problem downstream, we have an obstacle. If we release water, we are going to produce floods. So probably what they will do is, okay, we are going to shut down the gates, and we are going to release only a little amount of water to prevent flooding. So at that moment, we don't rely on the computer model anymore. At that time, we rely on the engineers that are in charge of the system. I'm not sure if that makes sense, William.
Yeah, it does. Thank you.
Thank you. So guys, continue with this. So we can control the flow rate through the turbine and the gated spillway, right? So we can control that, as I mentioned before. The overflow spillway, which means that the flow that passes above the spillway, we cannot control that. Okay, that's called emergency spillway or emergency overflow. Okay, so in this lecture or in our application, guys, we are interested in finding the optimal values for the turbine and for the spillway flow rates. Here, maybe I forgot to mention here, I should say here, this should be for the gated, spillway flow rate, right? Because that's the flow I can control. The spillway overflow that goes above the spillway, I cannot control that. Okay, guys, so we want to know what should be the flows, example, every 1 hour or every 30 minutes for the next several days, example, for 1 week. I want to know what are the flows starting today for the next week in such a way that I can make more money by selling the power, right? By selling electricity. That's the main idea. Okay. So guys, this is the schematic. So we can basically, every hydropower, we can basically have this system. So basically, guys, we have two types of flow, right? We have a turbine flow, which I can control, and we have the spill flow, which also I can control. Okay, so this is gated. Both of them are gated, right? Both of them are gated. And of course, on top of this, we have a emergency overflow. So if there is too much water, that water will pass through the spillway. So guys, typically in those cases, I am not interested in producing power anymore, because power will not become the main objective anymore. Flooding will become the main objective. So if you have too much water, if it's raining everywhere, your objective is not making money anymore. Your objective now changes to saving lives. So it's different, okay? So we will not talk about that, guys. We will talk only about hydropower here. Okay, so okay, guys, so the equation for producing hydropower is given by eta. It's called the efficiency. Okay, this is the efficiency of the hydropower. And the efficiency, guys, is typically 70 to 80%. This is the turbine. Okay, so typically the efficiency of producing power is 70 to 80%, depending on the turbine. Example, you have a Francis turbine, you have a Pelton turbine. Depending on the turbine that you use, depending on your design, typically the efficiency can change from 70 to 80%. Okay, guys, this is the value of density of the water, which is about 1,000 kilos per cubic meter. Okay. We have, guys, gravity. Gravity is 9.8 meters per second squared. Q is the flow discharge. The flow discharge in cubic meters per second. And H is the head in meters. Or also, guys, you can convert this to English units. Okay. But the formula is the same. So, guys, any question about this?
No.
Okay. Okay, so let me clear this. Okay. So, guys, we will start with one example of one dam. Let's, guys, assume that we have done the study and we are using a given type of turbine and my efficiency is 70%. Okay. Let's assume that. And then also, guys, the head losses is the head losses, guys, are the losses that happens by friction or by local losses. So I assume, guys, that everyone took fluid mechanics.
Yeah.
Okay, so you guys know what head losses means, right? Okay, so head losses, guys, are the losses due to the friction in the pipe, and losses due to gates, bends, valves, and so on. Okay, so typically, guys, the head losses is 10%. Okay, I'm here, guys, assuming because I want to make the problem more simple. However, if you want to apply this to a real system, you guys can calculate the head losses, right? Because you can apply for example, the Moody equation, and you can calculate how much losses you will have. And maybe you have a 8%, 10%, 12%, and you guys can correct that. But here, I don't want to do that, so I'm going to assume that my head losses are 10% of the gross head. What is the gross head? The gross head, guys, is the head is the difference of head between the upstream water level, okay, and the downstream water level. Okay, so if you have a dam and the downstream water level is this, and the upstream water level is this, the difference is going to be the gross head. Okay, gross head. Therefore, guys, here in this problem, my net head is going to be 90%. Why? Because 10% I am losing due to friction and local losses. Okay, so if I replace, guys, those values of efficiency and losses, then my energy will become this equation. Energy will be efficiency, density, gravity, flow, and net head. Okay, or you guys can convert to also gross head, because remember the net head is 90% of the gross head, right? I am assuming that. And then, guys, here we have some assumptions about the shape of the dam and all of those considerations. I will simply, guys, algebra. And then, we can express, guys, this as a function of the storage, because I am assuming that my storage is rectangular. So, you know, if the storage is rectangular, guys, the storage will be the area times the head, right, above the bottom. Then, if you guys do that, you guys can have this equation. Okay, and then, so guys, I can replace this equation by this equation, because here I have a Q, this is Q, and all of this times this becomes a constant, okay? And this is a constant, so this multiplied by this will become also a constant. So that's why I have this equation. So kind of this is in general, because we want to simplify this. Okay, and K1, if you guys substitute here, K1 will be given by this, and K2 will be given by this. Okay, and then guys, we can put some examples. Let's say the area of the reservoir is 200 square kilometers. Let's say the head between upstream and downstream is 1 meter. H0 minus HD is 1 meter, and then you guys have these coefficients K1 and K2. You guys can calculate those values. And then now, guys, because I have to do this every 30 minutes or every 1 hour, I have to, guys, discretize the power, right? And remember, guys, the equation of the storage is the storage, right? Changing storage, right, divided by time is equal to the sum of inflows minus the sum of outflows, right? That is what we can do. And of course, here is going to be a storage at the next time step minus the storage at the previous time step divided by delta T. It will be equal to the sum of inflows minus the sum of outflows. Okay. So guys, this equation is simply the same equation as the previous equation. So let's go back to here, and if you guys have this one, it's the same equation, so I can discretize. The energy at time t will be Q at time t, K1 is, so I'm simply, guys, discretizing, right? So, and example, if I want to know what's my energy at after 1 hour, it will be my turbine flow at the previous time step. Example, at time 0 hours, let's say I set up a given flow, right? A given flow, and then I have to multiply by the coefficient, storage plus K2. Simply, I am discretizing, guys. This is just to apply the equation. Okay, so the storage, guys, we use at the half time step. What does it mean that? Example, if you guys have a 1 hour, from time 0 to 1 hour, okay? Guys, the storage is not constant, right? The storage, whenever you are filling the reservoir, example, if this is at time 0 hours, okay, at time 1 hour, maybe the flow is going to be here. Okay, this is at 0 hours, maybe this is at 1 hour. Here, guys, what's going to be the average? What's going to be the average between 0 and 1 hour? Because that's what I am interested in. So it's going to be this one. It's going to be the average. So I can say the storage at 0 plus 1. So I have this storage. The storage I need to use from the calculation has to be the middle, right? So I can draw a line, and this is going to be my storage. And the same thing, between 1 hour and 2 hours, I can do the same. This is my storage at 1 hour, my storage at 2 hours. But the storage I am going to use for my model is going to be the average, right? The average. And here, the same thing and the same thing. That is what we use. This is what we use for the calculation of the energy. Okay, so okay. So guys, now the outflow. The outflow is is not evaluated at the middle. It's evaluated during the whole hour. So example, if you guys, let's say you have, this is, let's say, time 0 hours, okay? This is outflow, this is the outflow, and this is time. And then you guys want to operate the gate, let's say, every 1 hour, okay? Every 1 hour. You can say, okay, at time 0 hours, I want to keep the gate closed, okay? At time 0 hours, I keep the gate closed. And after 1 hour, I am going to open. I'm going to open at a given level, and I am going to keep the flow, right? So during the whole hour, you keep closed. And during the whole hour, you release a given amount of flow. And then after, you can kind of change. But as you guys can see here, all these variations are, in steps, are gradually. So during the whole hour, during the whole hour, you will keep the same flow, because you are keeping the gate at the same position, okay? Remember, you are operating every 1 hour, right? So you are not changing the gate in the middle of that hour. You are only changing every hour. Therefore, the outflow will be more or less constant. This is why we have this. It's constant here, constant, because this is during the first hour, during the second hour, during the third hour, during the fourth hour, and so on. Guys, any question about that?
Not from me.
Okay, guys, so then we can go back to that equation, that the discretization, right? And then we can start to do that. This is the storage for the this is the average in the first hour. That's why I put half, right? Because it's 0 and 1. I'm putting this storage at half hour. It's the average between 0 and 1 hour. So this will be the, if you guys replace the values, will be this one. The storage at 3/2 will be this one. So this is at 1 hour and a half. Okay, at 1 hour and a half. You guys can keep doing that. This is a storage at 2 hours and a half. You guys can do it. I'm doing this step by step. So if you guys do this, you will have this is 2 hours and a half. Then, guys, after you guys do the first 2 steps, you will realize that there is a pattern. There is a pattern. So for any time between time t and t minus 1, okay, between time t and t minus 1, this is going to be the formula for the storage. It will be this in loop, which simply kind of has its limit, and then minus this one minus delta t. This is kind of the formula, the general formula for any average time step between t and t minus 1. Okay, guys. Then we continue this. Okay, so we can see here. Okay, guys. So now the electricity also we evaluate at full time step. You might ask why? Because, guys, the electricity depends on the outflow, right? It depends on how much power is passing to the turbine. Remember, the outflow is constant during the first hour. It's constant during the second hour. It's constant during the third hour. Because the outflow is constant, then the electricity also has to be constant during that hour. Okay? So electricity also has to be constant during the first hour, second hour, third hour, fourth hour. Okay? That's why I have this one. Okay, so now, guys, we can also discretize the energy. Okay, because I have a turbine flow, K1 times S. So basically, guys, I'm simply replacing the formula here. This is electricity for the first hour, electricity for the second hour, electricity for the third hour. And then after, guys, I do that, I figure it out that, oh, they have a pattern. So the electricity at any time will be given by this formula. Okay. And then, so guys, now the the revenue is simply electricity times price, right? If you guys multiply electricity, example, at hour 1 times its price at that hour, plus the electricity, at the next hour, times the price at that hour, plus, if you guys do that, that is revenue. The revenue is the electricity, the kilowatts hour times the price, right? And the price. And simply, guys, the revenue is going to be this. The revenue is going to be the sum of hourly revenues, because every hour you are making money, right? You are selling. So the revenue will be the sum of those hourly revenues. I think you guys can guess what is going to be the objective function here, guys. What will be the objective function here? Maximize or minimize R?
To maximize it?
Yes, we have to maximize R, right? That will be the objective function, right? So guys, what we did in MATLAB is simply put these equations there, and then guys, I will show you that in a minute. Okay, so in this. Okay, so guys, if you put it in the form of equation, it's going to be R, it's going to be this one. Okay, it's going to be this, it's going to be minus, all of this stuff. But guys, now remember, I am doing this not only for 1 hour, I'm doing this for 1 week, right? So guys, in MATLAB, whenever you use MATLAB, you can use for loop. You can use for loop for every hour. But guys, that is not computationally efficient. We have to use matrix, or we have to use vectors. To do calculations, we have to multiply vectors. We have to multiply matrices, because we want to be more efficient in the calculation of that. Okay. So guys, the revenue is going to be this one, which I should maximize. But guys, the next part of this is simply to speed up the calculations. You guys can do this, and you can use for loop, but it will not be efficient. It will not be efficient because you guys are doing one by one. However, guys, what I'm going to do next is I am going to convert this to a matrix system. So all the calculations in MATLAB can be much, much faster. 10 times or 20 times faster. Okay, so now I guys can do that simply converting that. I'm converting, guys, to matrices and vectors. Okay, so these guys, I have a turbine flow. So here I have this is turbine flow 1, turbine flow 2, turbine flow N. Okay, and I have this is the spillway flow 1, spillway flow 2, spillway flow N. So N, guys, is the number of hours. For example, I can operate for, if it's 1 week, it will be 24 hours times 7, right? So I will have this number of variables. So guys, I am simply kind of doing the transferring to a matrix system. So in that case, if I do transfers, I will use, guys, the Hessian. And the Hessian is the second derivative of the objective function divided by x1 squared and x1, x2, and so on, right? This is just algebra, guys. I will not talk much about it. I'm simply doing this to kind of speed up the calculation, okay? And, okay, so guys, the same thing we can use also in MATLAB, guys. We can use also sim, which basically is a mathematical stuff rather than using computational. This also can save some time. Guys, I will skip this, guys. Example. So the way, guys, you can play with this, and actually I have done this, is you can have your matrix will not be a small matrix. Your matrix will be 2000 by 2000 or 3000 by 3000. So it will become huge. So you guys don't want to do that, because if you do a mistake, it will be very difficult to find out where is the mistake. Rather than doing that, I play with example. Let's say that n is equal to, I have only 2 hours. Okay, and everything seems good. Now I'm going to do it 3 hours. And with 3 hours, example, you guys can form your matrix. Okay, my Hessian, in this case, my Hessian is going to look like this. Because if you guys have a matrix of three variables, 3 variables, x1, x2, x3, which means I have a three turbine flows and I have a 3 spillway flows, so I'm going to have a 6 variables. Then guys, I can calculate a Hessian by hand. If I do by hand, I can check, I can check by hand and I say, oh, this has this shape, all of this will become zeros, so you guys can start to have the pattern. And then that's guys what I did, right? I have a for 3, and then here, example for 4 becomes like this, for 4. Oh, here becomes 0. So you guys start to see a pattern, right? And here, example, guys say, oh, here I realize that all of this is zeros. I realize that this is P1, P2, P3, P4. So you see, guys, it's repeating here, it has a pattern. And also here, these guys are kind of transposed. You have a P1 half here, P1 half here. You have here P2, but this P2 comes here, right? So they are kind of transposed. It's kind of flipped. So, example, this is H1, 2, and this is H2, 1, because it's flipped. So I say, okay, this H2, 1 is the transpose of H1, 2. Okay, and H2, 2 is equal to zeros. H1, 1 is sequential because, I have a 1, 2, 3, 4, 1, 2, 3, 4. Okay, so I said, okay. And I start to have a shape. I start to have a pattern. Right? I start to have a pattern. Okay, so we can do that. And then, guys, we simply do some evaluations in MATLAB. I do that to get kind of the pattern. And then, guys, that's it. And here, guys, we have the constraints. Okay, the constraints for the turbines is okay. The flow cannot be below 0, right? The minimum flow in the turbine has to be 0. So if you completely close the gate, the flow will be 0. And then here we have, okay, the maximum flow will be 25,000 CFS. Why is that? Because, every turbine has a capacity. So here the capacity of the turbine is between 0 and 25,000. The spill flow has to be as minimum 0, right? It cannot be below, it cannot be negative, right? The water cannot go from downstream to upstream, right? And then here, guys, there are some constraints for the turbine and the spill flow. The storage also has to be between this value and this value. So there is, guys, some constraints, right? There is some constraints. Okay, you guys know that the linear constraints are given in this form. Actually, we have talked about that. The bounds, guys, have a lower bound, right? We have the lower bound and the upper bound. And in this problem, we have 4 linear inequality constraints and 2 bound constraints. Okay, I will, guys, not talk about this because you guys know what are this. So I will, okay. So, guys, here we have those. You can define those. I will not talk about that because you guys more or less know how to do this. And I am simply, guys, specifying in MATLAB the constraints. Also, I don't need to talk about that. And I specify my play. Let's say I have 3 variables. With 3 variables, guys, or 2 variables, I start to play and I start to assemble the whole thing. So this is constraint 4, and I see how I assemble the whole thing. And here I'm playing it, to see how this is done. We will, guys, play once we start to play with MATLAB. Okay, so this is simply just testing and playing, specifying the constraints. Okay, and then, guys, this is the optimization. These are the options. We are going to use 5,000 evaluation, which method we are going to use, and this is how you specify the optimization. You have the initial condition, right? We have the initial condition. This is the matrix A. You have to specify the matrix A, and I will, guys, show you this in a minute. What's the B, right? Because AX is smaller or equal than B. A is a matrix. X is the vector variable, so I have x1, x2, x3, and I can have thousands of variables. And B is the value of those inequality constraints. Okay, so okay, guys. So once you run the model, you will have something like this. So this is example. First, guys, we will talk about with a very simple problem. Initially, we have a constant flow. Let's say the flow is constant. Okay. Let's say the flow that comes to the dam. So let's say, guys, the rain is constant, and the flow that comes from upstream is very constant, right? Okay. So this is constant inflow, right? Constant inflow, which means the rain is constant. Price. This is the price of the hydropower. This is dollars per megawatt hour. Okay, so it changes. You guys can see it changes. Let's say this is the variation of the price. And guys, if I have these two conditions, my optimal flow will be this. So this is the turbine flow. Turbine flow will be, okay, between 0 and 10 hours, don't produce power here, produce power a little bit. And then between 10 and 15 hours, produce a lot of flow. And here more, and here no power, and then here produce a lot of power. Okay. So guys, we will play with that. So I will, guys, ask you to please download the MATLAB code that we have in Canvas. And guys, we will play with this. Okay. So guys, why don't you take 5 minutes to download and open in MATLAB. The file is called main. The file, once you guys download it, the file is called main. So guys, why don't you guys take 5 to 10 minutes, and then guys,
Professor?
Yes, please.
Are you sure it's called main? Because I downloaded the hydroelectric dam optimization and I unpacked it, and there's like 10 or 12 files, but I don't see a main.
Okay, so let me guys show you. Let me open it. I will guys share with you what I have. Okay, so let me see. Okay. So let's see. You guys see my screen?
Yeah.
Mm-hmm.
Okay, so what I posted is this one. So I have lectures. I have a hydropower demo. Okay, and I posted this one, hydroelectrical dam optimization, which is the same as this one. Okay. So, oh, sorry guys, not main here. So first, guys, we are going to play with this one, hydroelectric dam optimization. That's the one we are going to open first, hydroelectric dam optimization. So guys, why don't everyone download this one, and if you have any problems, guys, you can show. Okay. Hello, guys. So, did you guys were you able to download and run that file?
Yes.
Yeah.
Okay. What about you, William and Guillermo? You guys?
Yes.
Okay, great. So, guys, let me run with you and go over this with you. Okay. So basically, guys. Okay. Let me open this file. Do you guys see my screen? No. Oh, okay. Let me share my screen with you. Do you guys see my screen?
Yes.
Okay, right.
Yes.
So here, guys, we have the constraints. As you guys can see here, we have the constraints, and here we have the load the data. So, guys, the data here is basically is the data of the inflow and the price. If you guys open this file, you guys will see that we have the price and the inflow. So also you guys can access the data from here. You guys go to the price. It must be here. And this is let's see, what is this? The name is flow and price. Let's see, where is this? I cannot access from here. But anyways, guys, you can. There is a. I will, guys, not talk about that, but there is a way, guys, where you can visualize this math file. So this is the name is flow and price data. It's a math file. But guys, this simply has the data of the flow and the price. And I think here I put the flow and price here. Let me see if I can find that one. I think I call inflow. Let's say here inflow. Here we have the inflows and the price as well. Here, the price is. This is for actually, guys. This workspace is for something different because I have to clean it. I have to run it first. So let me, guys, run it because this workspace corresponds to a different simulation. I was running for another problem. Okay, so now, guys, different. This is different. Okay, I'm going to close this one. So it's running, guys. It's running, and then hopefully this is going to update. Okay, so guys, we have to wait for a few seconds, and hopefully this is going to be updated. Okay, yeah, I think it updated. I'm not sure. No. So let me, guys, put clear all. Okay, CLS. Okay, I cleared all it, guys. So now you don't see anymore the workspace. So now, guys, I'm going to run again. Now, hopefully, I should have the new data. Okay, I'm running again. Okay, so we are running with the model fmin_conv first. So this is the iterations. We have iteration 1, and it's calculating the optimal releases. And now I am using the fmin_conv. Okay, so here, guys, here you guys see I have the price. You guys see here the price. So these are the values of the price for 50. This is for 50 times steps, right? 50 times 1. So you guys have 50 values of the price. Right? The same thing, guys, you have for the inflow. The inflow is going to be the same. If you guys click there, you guys have the inflow. It's constant, right? Because 1070 is constant. We said it's going to be constant, so here I have the flow, and it's constant, right? Okay. So now, guys, we are using two methods, or three methods, guys. Sorry. The first figure corresponds to this one. The first figure is so guys, we have a fmin_conv, right? We are using optimization algorithms called fmin_conv. The second one is F min con, but we are providing the gradient and the Hessian. So basically, we are giving to the model the derivative, the first derivative and the second derivative, right? We are given the gradient and the Hessian. And then the third one, guys, is the quadratic programming. Okay. So guys, this time is the time of computation. As you guys can see, the F min con takes 4 seconds. Okay. The F min con with supplied gradient and Hessian. So if you guys give the gradient and the Hessian, guys, this will take 11 seconds. If you guys use the quadratic programming, it takes 0.4 seconds. Okay, 0.4 seconds. It's very, very fast. It's very, very fast. So guys, when we do large scale optimization, we will not use the first two. We will use simply quadratic programming. Why is that? Because it's much faster. Okay, guys. So let me guys show you the results here. This is figure 1 with method 1, F min con. Second method, this is F min con with supplied gradient. And then the third method, guys, is with quadratic solvers. If you guys see, the results are pretty much the same, right? Do you guys see differences? No, I don't see differences, guys. The results are the same, basically, are the same. And then you guys will realize also the objective function is the same for the three of them. Okay, so the revenue, you guys can calculate here the revenue. With the revenue here. Okay, guys, here you have the revenue. You can see the revenue. So the revenue example, this is F, right? The revenue here is, I am putting here, I have here, guys, minus because remember in MATLAB, we always minimize, right? So if you want to maximize, it's going to be maximization is negative of the minimization. So the objective function here is F, which is, so the revenue is here 3 times 10 to the 4, 3 times 10 to the $4, right? 3.002. This is with F min con. The second method is 3.01, right? It's very close, guys. You can see here, the revenue is very close, very similar. And with the third method is also very similar, 3.002, right? Very, very close, very close. Okay. Okay, guys, any questions about this? And of course, if you guys want to see how we define those things, you guys can go to the main file here. Okay, we close this, And you guys will see that, okay, here I have the initial storage, okay, initial storage to 0, 5,000. The coefficient K1 is the coefficient that we have in the slides, 0.003. The K2 is equal to 9. M2, you know, and those coefficients, guys, are taking. So if you guys go to the defined constraints, right? Defined constraints. This is the constraints of the model. So if you go to constraints, we can see here defined constraints. If you guys open that one, you guys will see that here we are defining the constraints. We are defining the bounds, constraints, you know. But here, guys, I am doing in a matrix form. Why I am doing a matrix form? Because, you know, if I have 1,000 variables, you know, guys, I can simply define everything in a couple of lines. Otherwise, if you don't do this, you will need to define for every line. For every constraint, you will define one line, you will do for and loop, and it's very, very inefficient. But here, guys, you can do, you know, in a very quickly manner, you guys can, you know, can do the same thing regardless of how many, you know, how many variables you have. If you have a 500, 1,000, 2,000, the same, right? It's going to be the same. Okay, and then of course the objective function is here. You have the constraints and you have the objective function. This is the objective function, right? And this is the. Okay, guys. So,
excuse me.
Yes, please. Yes.
Yeah, I have a general question. So why we
Okay.
why we control turbines based on prices? Why we control prices based on turbine?
No, we do not control prices. What we control is the flow releases. Price we don't control. Price is given by the price is set by the market. So we only control the flow release, which means that how much flow passed through the turbine and how much flow passed through the gated spillway. We only control that. The price we cannot control. The price is given by the market.
Yeah, thank you.
Thank you. Okay, guys. So this is if you guys realized here we are only using 50 time steps, okay? Because we want to play with several models. We want to play which model is better. Is F-min Kong or dynamic programming? Which model is better, right? So here, guys, we find out that the model that is the best is quadratic programming. Why? Because the computational time is only 0.4 seconds, right? 0.4 seconds. Now, if you guys want to do this for not for 50 time steps, but you want to do this for, 2,000 time steps, like let's say you want to do, guys, every 10 minutes for 2 weeks, then, guys, you will have many decision variables. If you guys want to use F-min Kong, the optimization will take 1 day or 2 days, right? So you don't want to do that. And then remember, guys, you have to sell the power every 30 minutes or every 20 minutes, or sometimes even every 5 minutes. So you cannot use a model that gives you results in 1 day, right? So here, guys, we have to use the model, the quadratic programming model. This is going to be very, very fast. So if you guys have a problem, example, for 2 weeks, every hour, this model will give you results probably in a couple of minutes, maybe 1-2 minutes, okay? Which is reasonable. Okay, guys, so now we are going to use only quadratic programming model for a real system, okay? For a simulation of 2 weeks. So, guys, now please let's open the file. Guys, before that, let's let's put close all and clear all. Okay? I'm going to put clear all also, because we want to make sure that all of this is deleted before clear all. So, guys, now we are going to open the file hydroelectric dam optimization large scale. So this is an application for a large scale with a period of 2 weeks. So here, guys, now we put clear all. Okay. So, guys, let's run the model now. This is the model. Then, guys, we are going to run this model. But now, guys, we are running, guys, for a period of, okay, guys. So now you guys can see that the simulation was very, very fast. This is for a period of 20 days. 20 days. Okay, 20 days, every 1 hour. And it was very, very fast. Why? Because we have used dynamic programming, which is the most efficient solver, right? So, guys, the price of the market is given by this, okay? This is the price of the market. We are not optimizing that. This is given. This is data, okay? This is, guys, the total flow release in the turbine, okay? So you guys can see that you have a, typically you don't produce too much power, you produce little power, and then during some peaks, you produce power. If you guys can see, basically, when the power is higher, you are producing power, and at some points, you are not producing too much power, right? So, guys, this is the storage, right? The initial storage is 9 million acre feet, right here, 9,000 acre feet, and then it goes up, and then it basically you have to go back to the same storage. You guys can see it here, and this is the optimal turbine flow, the cumulative of turbine flow. Guys, can you please try to run this and see if you are able to run and see if you have any questions here?
I had to download a symbolic math toolbox. I'm still doing that, unfortunately.
Oh, okay.
Yeah,
Yes,
same.
guys. Okay, yes.
I was able to run.
Okay, great. Oh, yeah, because I think maybe you, in the previous time, maybe you downloaded a sim file. But yes, this particular problem will require the sim add-on of MATLAB. Okay, guys. So here, example, you can see that the optimal revenue. The optimal revenue is 3 times 3.10 to the 5, right? 3 times 10 to the 5, that's the revenue. 3 times 10 to the 5 dollars. That's the revenue here. Now, as you guys can see that, at the beginning you start with minus 2.9 million, and then it goes down, and it's iterating, right? It's iterating. And after some time, it will converge to a given value, right? In this case, 3.25 to the 5 dollars. That is the optimal revenue. And then, guys, here we have the definition of the. So if you guys see here, this is just a figure, the position where I want the figure to be. This is how many days. Okay, this is depending on the price, right? If you guys see here in the price, I have how many hours of data I have. I have 480 hours of price, which is 20 days. I have a 20 days of price of power. Okay, so 20 times 24, it should be 480. So I have a 20 days of data of price. Inflow, in the same way, guys, this is my data. Oh, yes, it's changing. The inflow is changing. So you guys can see here, the inflow. This, guys, is the inflow. You guys can see the inflow is changing, right? So guys, in real life, the way how this works is that, example, if you are planning for hydropower production for the next week, first you have to forecast how much flow, how much rain you will have in your system, right? And with that rain, you can calculate how much flow you will have available, right? If you are wrong in your prediction, then you will not make much money, right? Because you can say it's going to rain in the next 3 days and I am going to have this flow. But if you are wrong, you are going to lose money, right? Because, or sometimes might happen the opposite, right? So it's important to make good hydrology predictions. So here we are assuming that we have made these predictions. And, I am assuming that this is correct. And if I have this inflow, and my future price is going to be like this, so also we have to do a forecast of price, right? So we more or less know that during the day, at some times the price is going to be much higher. We know that, but we don't know exactly how much it's going to be, right? So here also we can do a forecast of price, and people do these models. So people of econ, typically they do these models, and these models are available, like in hydropower, in the Bonneville power. They had these models, and they would give us these models for making, for us to use it in the hydropower operation. Okay, so this is the price we are assuming that we have, and we are also assuming that we have an inflow, and then, guys, with that, for optimal turbine flow is going to be this, right? For the 20 days, every hour, right? Every hour. And also, it's telling me here the optimal spill flow is what? 0. Right? The optimal, according to this model, is telling me, hey, during this time, you do not need to spill anything, which means that if you are going to put water from upstream to downstream, it has to be through the gate, right? Through the gate, because you want to make more money. However, during flooding, or whenever, if you are going to have too much water, the model might tell you, hey, you need to put some water in the gated spillway. Why? Because you will have too much water, so you might produce problems. Or maybe if you need constraints, right? Maybe if you have to satisfy constraints. In this case, it's asking me to not to put any water in the gated spillway. Okay, and this is, guys, the variation of the storage. The variation of the storage in the 20 days. This is 20 days. All right. Okay, guys. Any questions? Can you please try to run this model and let me know if you see any issues?
I'm just still trying to get the symbolic toolbox. I just opened MATLAB again, so I'm going to try now.
Okay, sounds good. By the way, guys, here I have defining constraints, right? Storage, initial storage is 90,000. The value of K1 is this. The value of K2 is this. This is just to convert from megawatts to kilowatts. Okay. Remember, a kilowatt, guys. A kilowatt is 1,000 watts, and a megawatt is 10 to the 6 watts, right? So to convert megawatts to kilowatts, I have to multiply by 1,000, right? Because it's 10 to the 6 divided by 10 to the cubic, so it's 1,000. This is for converting from CFS to acre feet per hour. So this is for the storage conversion, right? So I'm using those coefficients. And then, guys, remember, in this case, I am only using quadratic programming. Why? Because quadratic programming is the more efficient, right? We have found that in the previous simulation, we have found that quadratic programming is more efficient in terms of computational time. So, guys, I want to minimize this function. Minus half times the x, which is the decision variable, times the Hessian times x. It's x transpose. X transpose Hessian x, right? Minus f. All of these, guys, all of this is defined in the PowerPoint presentation, right? Okay, so we have a turbine flow and we have a spill flow. And here, guys, here I am defining everything. I have H11. You remember H11, guys? So we have a P1, P2, P3, P4. Here I can have 1,000, and it will go P5, P6, right? And then I have a P1, P2, P3, P4, the same thing. H12, guys, H12 and H21 are transposed, right? So here I have H12, has this shape, and H21, guys, the transpose. H22 is 0. You guys remember? H22, all of them were 0. That's why I have it here. And then here I am initializing the matrices. Initially I start with zeros, and then after I put zeros, I start to fill these values, P1, P2, P3, P4. So here, guys, I start to assign. So if you go back to the slides, you will see that H11 will be, I'm just basically, guys, filling up this. I'm filling up this one. And H21 is the transpose. And then, guys, I have to have the general Hessian. The Hessian is H11, H12, and then H21, H22. And then, guys, I am building my Hessian, right? And then this is the F, the same thing for F, and I have the in loop, right? You guys remember the in loop 1, in loop 2. This is for in loop 1 hour, 2 hours. But I guys, yes, please, yes.
Sorry to interrupt you. I'm still getting an error that I require symbolic math toolbox, but I just installed it. It's also saying that in line 65, x equals sim, the turbine flow, and it just says error in there. I'm not really sure why.
Okay, sometimes this happens because can you please save your data and close MATLAB and open it again?
Yes. So I'll do that.
Yes, that's what he told me to do. After I downloaded the same math, he told me to close the app and open it again.
Oh, okay. I mean, I thought I did that honestly, but we'll try. Thank you.
Okay, guys. So then, as you guys can see, we have the in loop for 1 hour, for hour 2, for hour 3. I did that for hour 1, 2, 3 hours, just to figure it out. What's the pattern, right? Then after that, for the first 1 hour is this one, right? But then for hour 2 to hour n, which I can have here, I simply use the for loop, but then I follow the in loops and the F2s, and I am filling basically the objective function, right? And then I do the conversion from megawatts to kilowatts, and then this is the matrix of F. And then, guys, I have to define the constraints. If you guys open the define constraints, you guys can define, the constraints for that are specified in the model for storage, for levels, and everything. And then, guys, I'm going to use the algorithm, right? I'm going to use dynamic programming, and I use quadratic programming solver, right? Quadratic programming solver. And this is the options. This is the options of the quadratic programming, right? I'm going to use the interior point convex method, which is a method of quadratic programming. This is the H. So if you guys see here, H, the Hessian. Okay? F prime is here. So I have a F, and F, this is the derivative. This is the derivative here. A is the matrix, right? B is the, remember AX is smaller or equal than B, right? So this is the first. So this is AB is inequality constraints. AEQ and BEQ are equality constraints, similar to what we have done in class. Is that wrong? Okay. LB and UB, it means lower boundary and upper boundary. So this is the boundary that you specify for the decision variables. And QOPTS is simply the options for the quadratic programming. Okay. And guys, then I have to display the results, right? The results, turbine flows are the first flows from X1 to N, and the spill flows will go from N plus 1 to the N, which means N plus 1 to 2N, right? So the first N flows are turbine flows, and from N plus 1 to 2N are spill flows. And then, guys, we create the plots, right? We have the plots of turbine flow, spill flow, inflow, price, storage, and everything. And then if you guys run that, you will have this, right? Or you guys can, what you guys can do as well is run it again, and then you guys can see now it's running, the iteration. It's very, very fast. It ran only in 4.7 seconds, right? So this is, guys, the inflows again, the inflow discharge. This is the price, electricity price for the 20 days, every hour. And then, guys, this is the optimal results. This is the optimal flow. So basically it's telling you here in this model, produce power at this hour, and then at this hour we produce this power. So this is trying to maximize the revenue. And of course, this depends also on how much water you have available, right? How much water you have available. Okay, guys. So this is pretty much the hydropower. Now, if you guys want to apply to a particular problem, you guys can modify, the data. But pretty much the algorithms for the constraints and the objectives are pretty much defined here in the MATLAB. You would simply need to change the storages, initial storage. You would need to change the coefficients K1 and K2 because that depends on the area. But basically, the whole setup of how to set up the Hessians, the Fs, all of that stuff is general. So if you guys change your problem, you guys don't need to change the H or the F because that is kind of a general formulation. So Guillermo, you were able to run this, right, without any problem?
Yes, I was able to. Yeah.
Okay. Do you have questions? What about you, Olivia? Were you able to run the model?
Yeah, it ran fine after I downloaded the add-in.
Okay, okay, great. Do you guys have questions? Or Abbas, did you run the model?
Yeah, already run.
Okay, okay, great. Do you guys have a question on this?
No, I mean, I
No.
think the concept's clear, but I definitely need to practice my MATLAB.
Yeah, so once you start to apply to a particular case, my suggestion for hydropower and for flood control is because here in this case we have 20 days, okay, 20 days, and we have decision variables every hour, okay, so 20 times 24, we have 480 turbine flows, right, every hour, plus 480 speed flows, speedway gated flows. So we have 960 variables, right? 960 variables, 960 decision variables, and it was very, very fast. So if you guys check the matrix of this, the matrix is going to be very large. Some matrices will be 480 by 2000, right? So 480 columns and 2000 rows. It's a huge matrix. So if you guys want to detect a problem there, it's almost impossible. So typically, guys, whenever you are doing this, what I suggest and what I have done actually is you simply assume, let's say you have two decision variables. Okay? Let's say you have two turbine flows and two gated flows. And then you guys do it by hand. Once you guys do by hand, you will realize some pattern. Then you do for 3 hours. And then guys, once you figure it out the pattern, you put that in MATLAB. And that's it. So in that way, guys, it becomes easy. But if you kind of start from scratch and put everything in MATLAB, it's kind of difficult. It's better to do first by hand, and then once you kind of figure it out, the pattern, it's guys easy to put it into MATLAB. Okay, guys. Here also we have Hector. Hector, were you able to run the MATLAB?
Hi, Dr. Leon. Unfortunately, I log in until six quarter, so I haven't running the model.
Okay. So we have the model in Canvas, so it would be great if you can try to run, and if you have any problems running, please let me know, and I can try to help you. Okay, William, were you able to run the model?
Yes, I was able to run it. I'm not seeing all of the same things, I don't think, but it might be because my computer's slow and it's still running some of it.
Okay.
Actually, no, it did run it, but I don't see like the electricity price and optimal flow like you're showing there.
Okay, so you would need to run the hydropower large scale. I think you opened the first one. So maybe can you open the hydropower electricity large scale? That's the name of the file. So basically,
okay, that's why. Sorry, that's why. I thought it was supposed to just happen for this one. Yeah, so that makes sense.
This one, maybe I should change the name here. Small scale. So I'm going to change the name here. So this one is a small scale, just kind of to figure it out which one is the best model. Small scale.
Yeah, that worked.
Okay, great. So that's a small scale, just to figure it out, the CPU time, which one is more efficient, right? So here is CPU time. Okay. Okay, guys, so now let's go back to the presentation. Okay, let me see. Okay, so okay. So let me guys share my screen. Okay, do you guys see my screen?
Yeah.
Okay, right. So now, guys, we have basically this is what I have done. Example, we have also some equality constraints, right, for the storage conservation. Sum of inflows minus sum of outflows has to be equal to the change of storage in a given unit of time, right? So for that, A cube, B cube, sum of inflows. I am basically setting up that, right? I am doing it with a small variables, in this case, n is equal to 4. 1, 2, 3, 4, 1, 2, 3, 4. Yeah. So here I have eight variables because I have 4 turbine flows and 4 split flows. So this is, guys, how you define the objective function using fmin_com. Actually, this is in MATLAB, but here I simply copy that. And this is the result using fmin_com. Now, if you guys supply the derivative, the first derivative and the Hessian, which is the second derivative, you guys also can do it this way, okay? And then, okay, so this is the continuation here, how many evaluations you are using, maximum iterations and all of that stuff. And then, guys, we have the quadratic programming solver. So now, if you guys use a quadratic programming solver, you have to define the function of this type. So then this is how you guys define it, the Q options. This is in MATLAB, by the way. Here I just copy this one, and the results will be pretty much similar. If you guys compare the results, basically you guys notice that the quadratic programming is much faster because the simulation is only here, in this case, 0.2 seconds. If you guys supply the first derivative and the Hessian, if you guys simply use fmin_com, it will take 3.5 seconds, right? So with the quadratic programming, you can do it much faster. Okay. Okay, now, guys, we can apply this to a large optimization, right? A large optimization. Here I have, guys, the price for 20 days, every hour. And then we have the inflows, which means the flow from the rain going to the reservoir, also for 20 days, every single hour. Right? It could be every hour, but sometimes it's constant, it's changing, but it's for 20 days. It's for 20 days, right? Okay, and this is the constraints, the storage, coefficients, the conversion factors, and so on. So here, guys, I am simply forming the x, h, and f prime, the first derivative, the Hessian, right? Because the model asks me to specify that. So here I am setting up the Hessian, right, for N4. Here, guys, this is for N4. Why I am doing this? Because I want to know how the Hessian looks like. I want to know how F looks like. Right? So that's why I'm doing this. So I'm forming the F, and then you guys can see here how I am setting up in the computer this one. The constraints, right? We are defining the constraints. And then this is a solver, how to set up the solver, and then display results. So this is, the solver is called quadratic programming here, quadratic programming, right? It's called quadratic programming. And then you define the Hessian, you define the derivative, the AB, which is the AX, this is a matrix, A, this is the vector, is smaller or equal than B. So the A will become a matrix like this, X will be the decision variables, minor or equal than B. And this is the equality constraint. So now you have again, this is a EQ. Now you have a X, EQ, X the same, is the X, the same X. And now it's equal now. And this is a vector called BEQ, right? This is BEQ. Okay, so guys, we are setting up that one. And then we have, guys, the results for that. Right? Have the price, the optimal turbine flows, and the optimal split flows. And then here, guys, we are comparing the CPU times for various solvers, and then you guys can see which one is better, right? So we find out that the quadratic programming solver is much faster. So actually, guys, in the case of the Bonneville Power, right now they use a quadratic programming solver because it's much faster. Okay, guys, so I'm not sure if there are any questions.
Not from me.
I have one question, but it's kind of general.
Yes, please, yes.
Like, for this section, for example, like for the final exam, how would we study for this? Like, what would you test us on for the final exam for something like this?
So for the final exam, actually, guys, we will talk about that a little later. The final exam, first of all, can be take home or can be in class. You guys have the choice. We will talk about that. Maybe you guys will vote. But typically, in the exam, I will not ask you this. In the exam, what I'm going to ask you is your general understanding of the class. Example, if I give you a take home, if you guys have a take home, I will give you one problem. I will say, okay, example, this is a model, or this is a calibration, or this is a data, and I will ask you, okay, formulate optimization problem, define the constraints, and solve it. Right. So basically, you guys, if you guys have the models and if you guys have the data, you guys should be able to solve the problem and discuss, if your results are correct or not. Right. Example, some of you guys in some homeworks, some of you got different solutions. Why is that? I mean, one reason could be because you are using a different initial point, right? So sometimes, guys, the optimization can be global, right? Can be global optimization problem. So you are finding a local solution. It might not be, So you guys have to check many things. It's not only defining the objective and constraints. You have to know how to recognize if your model is global or not. So you have to kind of use multiple starting points, right? If all the multiple starting points gives you the same solution, then your problem is, it has a single. It is not. Basically, you find the global solution, right? But if you change the initial point and you have a multiple solutions, then that's telling you that you have a multiple local solutions, right? So for the exam, guys, I will not formulate this. For the exam, I will give you one simple problem. Perhaps I will give you data of. In the past example, one problem I gave. I have a dam, and then I have a flow releases. The flow releases more or less fits this curve. A times B Q to the power of this. Find the coefficients A, B, and C that fit best the data. So basically, you are using kind of a calibration, right? And of course, you have to use a MATLAB or Excel, right? Example, if I guys ask you that, okay, let's say, so basically, guys, I give you a bunch of data in Excel, okay? I give you a bunch of data. Flows, levels, and I give you data, and I say, okay, example, the flow more or less describe the data K1 times head times to the K2. This is the flow, coming out of a dam. So I tell you, okay, more or less the flow can be represented as K1 times the head times K2. I will ask you, what are the values of K1 and K2. So basically, guys, you have the data. The data basically is telling you this is a Q and this is H, right? But I'm saying, okay, the flow can be described as K1 times K2. So I ask you, what are the values of K1 and K2? What do you guys do? Example. Simply you will say, okay, I want my model to be as close as possible to the data, right? So the model should be pretty much doing this, right? So if the blue line is my data and the red line is my model, a good model will be when the data minus the data is as close as possible, right? So you guys can say, okay, example, I'm going to minimize the value of Q, right? This is a model minus Q of data to the square. Right? You can do example minimum squares, or you can do this model, or typically people, you can do a least squares method, right? Least squares method. So what you do is you can use genetic algorithm, or you can use other methods. You can use that, and then the model will iterate until this value is the minimum, and then you will find the value of K1 and K2. Now, once you plot it, your model and data should be as close as possible. Should be very close. That's kind of one question I ask. Another problem I asked before is about a tidal. I say, okay, the tidal, this was for Houston. This one when I was in Texas. I asked, okay, the tidal in Texas is given by, follows this variation. So I give them the data. So this is the tidal fluctuation in this particular site in Texas. So I give the data, and I ask, also we know that the tidal can be described as a coefficient A, sine W is a frequency, times time, plus a coefficient B. And I ask, okay, and this is an example, this is the head, right? This is the tidal, elevation, right? The water elevation is A sine WT plus B. And I ask you, okay, find the value of A, W, and B. Okay? Find the value of A, W, and B. And then what you guys do is simply now you use, again, you want to minimize the tailwaters from your model. So tailwaters from the model minus tailwater of data, right? Some kind of measure. It's kind of a least squares too. You guys can use least squares. So this is kind of a calibration. Or the problem can be, if it's take home, could be, okay, you have this problem, okay, and then I can ask you, identify what will be the objective function, what will be the constraints, and then see, assume some values and solve it, right? It will be very general. So I assume, guys, that at the end of this class, you guys should be able to formulate a problem, define the constraints, define the bounds, and then solve it, and basically know if your solution is correct or not. I don't know if...
Dr. Leon?
Yes, please. Yes.
Well, from my point of view, my principal concern is that if we are going to apply MATLAB, I don't know if in some part of the developing of the test we are going to get stuck because we don't have a programming background using MATLAB. And most of my classmates as well. So I don't know how complicated it should be develop a MATLAB script for the exam.
Yeah. So you guys don't need to know MATLAB. So all the problems, the exam and everything, you guys can solve it using Excel. So you guys do not need to use MATLAB. So if you guys realize homework number 1, 2, 3, and 4 can be done using Excel. The exam, if I give you a take home, you guys also can solve it using Excel. You guys do not need to use MATLAB. I mean, MATLAB is much more convenient, and in my opinion, it's more, you guys can...
Algorithm in Excel?
I mean, in Excel, it's the same thing. In Excel is, so if you guys have in Excel, you have list squares, right? List squares. So you simply define, okay, this is my data, row 1, 2, 3, 4, 5, and this is your model. And the model is simply a formula, right? Model is simply a formula. So you are reading values from this one, and you have this one. And then your objective function is, okay, is this one minus this one to the square. This one minus this one to the square. You can copy this, and then this is the sum, right? This is the sum. So you have to minimize this. And you can do this in Excel, right? So you can say, okay, I want to minimize this by changing this, right? By changing, so it's going to be the same. So you guys can do this. You guys can do this in Excel. Actually, Excel it will be even more easy because Excel has a built-in like list squares function.
Okay, and can we apply genetic algorithm in Excel?
Yes, you can. You can.
Okay.
Excel has three solvers, I believe. It has nonlinear, genetic algorithms. Yeah. It's evolutionary optimization. Yeah, it does. Yeah.
Professor, so I wasn't here last week because I was at the conference. Can you provide me any more details about like what is required of the project, like what you expect of us?
Yeah, for the project, you guys can focus in any problem you like. In particular, if you are working in your research or if you are working in your thesis, or you guys can focus on that problem. So it's kind of open-ended. Or you guys, if you like, you guys can choose any of the homework problems that you guys were given and you guys solved. But this has to be more in depth because in the homework, it's everything is specific, right? But in the project, it needs to be much more. You guys need to define the constraint in detail. You guys have to use at least two solvers, and compare them, and then describe why you choose those two solvers. I mean, why those solvers are relevant for the problem you are targeting, and then discuss the sensitivity analysis. Sensitivity is not simply changing the values and saying, okay, here you go, right? This is the values, but we have to define how the results are sensitive to the variations, and then you have to also define, how do you know your solution is correct? Is your so basically, it has to you need to have a better understanding of the problem you are addressing. It's not simply like a homework. In a homework, you simply focus. Okay, I ask you, okay, what are the optimal values? Right? You simply find the optimal values, and that's it. But here, you have to kind of go into more detail. Defining the problem, the constraints, sensitivity analysis, and also, how do you know your solution is correct, right? And actually, what I'm saying now is written in the description of the project. So there is one-page description what I expect from you in the project. But the problem can be chosen. I mean, can be chosen by you guys. You guys can choose any problem. I mean, even though the problem is not water resources, you guys can go ahead with that.
Okay, thank you. And then are we required to use MATLAB for the project?
You guys can use Excel or MATLAB or any program you like. I mean, if you guys, example, can use Lingo, you guys can use Lingo. Some students in the past have used Lingo. So there is no requirement about a particular software. You guys can use any program you like.
Okay, thank you.
Thank you. Guys, any more questions? So guys, yes, please go ahead.
No, I was saying that nothing. Thank you.
Okay, guys. So I wanted to kind of show you what we will do next class. It's going to be, so we will do a flat control, guys, and so this is Hec Ras, and then guys, we have now forecast of rain. I will guys show you the programs that we use for that, and this is example some forecast that we will do in real time. we are going to apply, guys. This is the building of the HMS. This is the the HMS model. That, okay, I don't know. Let me guys see. Oh, you guys don't see my screen, right? So sorry about that. Let me guys share my screen. Let me see if I can. Okay. Okay. Do you guys see my screen?
Yeah.
Okay. So okay. So guys, let me go back. So guys, next class we will talk about flood control, but we will guys kind of see. We will talk about the hydrology model, the hydraulics model, which we already talked about, which is going to be Hec Ras. And then, guys, also the predictions of divided rainfall. So we will know the variations of rain in the watershed. We will talk about the applications. We will talk about in a watershed in Texas. This is a project that my group has done. So we will apply to that. And I will talk about how we have developed a hydrology model. And then you guys will play with the actual model for that Texas watershed. And I will guys talk about, this is the data that we can generate, the data of the rainfall every 1 hour, the curve number, the variation. This is the watershed. And then you guys will play with the HMS model. You guys will start to produce inflows, how the storage changes in the wetlands or reservoirs. You guys will play for that and see the flows in the rivers. And then we will talk about, guys, the optimal values, and you will see, guys, how we can generate the optimal releases of multiple. Now it's not only one dam. Now I believe it's 8 dams. So we will see 8 dams, and now we have thousands of decision variables. We have a rain that we are predicting in real time. So, guys, this will take us a couple of weeks to finalize, because we will talk about the hydrology model, and we will talk about the several stages. But and then you guys will be able to run MATLAB here, play, guys. So I will, guys, show you about the hydrological model, the hydraulic model, the links, and then in this case, guys, MATLAB is going to automatically run Hec HMS, Hec Ras, not once, not twice, thousands of times, and it's going to iterate, right? So also we will use about parallel computing. I will, guys, show you how to do that, and you guys will play with using MATLAB. Actually, guys, I should mention that one advantage of MATLAB is that MATLAB is good for visualizing, and if you guys want to convert it to C++ or to Python, you guys can convert from MATLAB. So let's say in the future you don't want to mess with MATLAB, you guys can convert to C++, or you guys can convert to Python, because most of you, I believe, use Python. So you guys can convert to Python, and some of you are familiar with C++. So you guys can convert from MATLAB to C++. Okay, guys, so this is all I have. And if there's any questions, starting, guys, next week for about 2 weeks, maybe at most 3 weeks, guys, we will talk about flood control. Okay, guys. Any questions?
Dr. Leon?
Yes, please.
By the way, have you used MATLAB in combination with EPA Swing?
Yeah, we can use that, but I haven't used. I have the code I wrote. The code I wrote is for Hec Ras, for Hec HMS. So we can automatically. It's not only running, but you have to change the values of Hec Ras and Hec HMS in real time. So you run the model, you get the results, and then open Hec HMS and Hec Ras automatically but you open in the background. You don't open the actual model. You simply open the files, the text files, in the background and run also in the background because you are running simultaneously multiple times. I haven't done for EPA swim, but I believe people have done it for EPA swim. I'm not sure. Okay, guys. So if there is no questions, guys, I will see you this Thursday. In 2 days, I will guys see you in person. I will guys see you in person in the engineering center.
All right. Thank you, Professor.
Thank you.
Thank you, guys. Thank you.
Thank
See
you.
you.
Bye.
All right, Professor. See you Thursday. Bye.
You too, guys. Bye-bye.